Hello everyone, we continue the study of PTAT voltage references. In our previous video we built this circuit which had this differential VD minus VD1 voltage as a PTAT voltage reference. In this video we will build a single-ended PTAT voltage reference. Please notice that in my previous video I put a diode connection on M1, here I put it instead on M2. For this particular circuit, it is not important which of these transistors would be in diode configuration. But for the next circuits that we are going to build, it turns out to be important. So I choose to start with diode configuration on M2. So the first step would be to build a PTAT current reference, and then we will use that to build also a single-ended PTAT voltage reference. How we can build a PTAT current reference? The simple idea would be to apply the VD minus VD1 voltage, to apply it on resistor R with resistance R. And if we assume that this resistor has a zero temperature coefficient, then the current in this resistor, which would be VD minus VD1 over R, since the VD minus VD1 is PTAT, then the current would be also PTAT. But how to do this? How to achieve this? How to apply the VD minus VD1 on this resistor R? One might use this naive approach to put the resistor exactly between these two differential terminals. And let's see what will happen. So let's draw the circuit again. We have the M1 and the M2. We have the diode here and diodes here. It's called D1, D2 to Dn. And this is all grounded, and we put the resistor like this. Now the problem with this circuit is that the moment we add this resistor between these two terminals, it behaves completely different from what we have here when the resistor is absent. The reason is that, so we have this current mirror here, and we have two currents flowing here equal to each other on the left and the right, and so this current comes here and it branches. Some part of it flows to the diode D, some part of it flows to the resistor R. And so, since the resistor is also connected to the right part, then it comes and joins with this current flowing from M2. So here it joins with current with M2, and it flows then to these diodes from D1 to Dn. So it's obvious from this picture that the total current for these diodes D1 to Dn is bigger than the current in the diode D on the left. And that was the important assumption, that the currents are actually equal to each other when we derived this formula. And since this is no longer true, then this formula does not hold, and there is no guarantee that the VD minus VD1 here there is no guarantee that this is PTAT. Therefore, this approach doesn't work. The second approach, which is slightly better, is to put the resistor here. So In this case, on this the bottom terminal of the resistor, we have voltage VD1, and if the voltage on the top terminal of this resistor was VD, so this voltage was equal to the diode voltage, the voltage on the diode D, then of course the current in the resistor R would be PTAT. However, again, there is an issue here, that there is no reason to, it is not guaranteed that these two voltages are equal to each other, because all we know is that the currents on the left and the right are equal to each other, but this does not mean that the drain voltage of the M1 and the drain voltage of the M2 would be equal to each other. So this also seems that it doesn't work, but in fact, with a simple modification, we can actually make this work. And let's now do that modification. So first, let's move this part a bit down. We will add here additional NMOS pair. Let's call it M3, M4. And let's put the resistor here. So this is the resistor R. So now let's prove that indeed the top terminal of the resistor R here, this voltage is equal to VD. To do that, first let us choose the sizes of M3 and M4 to be equal to each other. So W over L3 is equal W over L4. Now notice that the current of M3 is equal to the current of M4. This is because the current in M1 is equal to the current in M2, which we can denote by I. So now, since the currents in M3 and M4 are equal to each other, and the sizes are equal to each other, then it means that the gate source of M3 is equal to the gate source of M4. But since the gates of M3 and M4 are connected to each other, then it means that the sources of M3 and M4 are equal to each other. So we can write that source of M3 is equal to the source of M4. Now we notice that the source of M4 is the top terminal for the resistor R, and it is equal to the source of M3, which is the diode voltage of the diode voltage on the D. So this voltage would be VD. Therefore, the current in resistor R is VD minus VD1 over R. And since VD minus VD1 is determined by this formula, again, because the currents on the left and on the right are equal, so the total current that flows into these diodes from 1 to n is equal to the current on the left, then that formula holds, and so we can write that VD minus VD1 is log of n times k over q over r times t. And so from here it simply follows that the current I is PTAT as well. Next, we will use this current to build single-ended PTAT voltage reference. So for this purpose, let me first copy this circuit that we built here. So let's paste it over here. Let's drop some notations. So what we do next, so we know that the current that flows into this resistor R is PTAT. So what we do next is we add additional current mirror here. So let's call it M5 with gate connected, of course, like this. And we put here additional resistor. Let's call it R2, and we connect it to ground. Now, also let's call this resistor R1. So this is R1. Let's call it everywhere R1. Yeah. So in this circuit, we know that we already knew that these currents are equal to each other. It's denoted I, and that's the current that flows in this resistor R1. And since this is a current mirror, then the current in the device M5 is also I, and it flows into this R2. So the voltage on R2, let's denote it as VR2, would be equal to I times R2. So let's plug also the current, which we already know. It is log of N times K over Q times R2 over R1 times T. And notice that this coefficient in front of T is positive. Therefore, the VR2 is PTAT, voltage reference. And again, the VR2 is the voltage with respect to ground. So we achieved a single-ended PTAT voltage reference. So I would like to finish this video with a comment about the temperature coefficient of R1. As you remember, we made an assumption that R1 has a zero temperature coefficient, and that was important for the current I to be itself a PTAT current reference. However, for the VR2, it is not an important assumption, because even if R1 has some kind of a temperature coefficient, and we assume that R2 is a resistor made from the same material, so it will have also the same temperature coefficient, then the R2 over R1 would be temperature independent, even if R2 and R1 both have the temperature coefficient. And with this, I would like to finish the second video on the voltage PTAT references. Thank you.